Hi, good morning. It's time to do some questions on electric circuits. So you've learned some equations, you've learned how the rules for current and potential difference of resistance work in a circuit. Now it's time to test some of those rules. But to begin, a little starter. What are the units for the following quantities? Resistance, current, voltage, charge, time, and energy. What is the equation that links current and time and another quantity? And then what are the rules for resistors in series and resistors in parallel? So pause the video, answer the questions, and unpause when you're done. You done? Excellent. What are the units for the following? So resistance is in ohms, OHMS, and it has this little symbol like that. Current is amps, and we just have a capital A. Voltage, potential difference, volts, is V. Charge, I shouldn't write charge, I should have written coulombs. That's going back to the beginning, and that is measured in C, and time is in seconds, and that's measured with an S, and energy is joules, and that's with a J. What is the equation that links current, time, and another quantity? Q is equal to I T. Charge is equal to current times time. And what's the rule for resistors in series and the rule for resistors in parallel? Series, it is total resistance is just resistor number 1 plus resistor number 2 plus resistor number 3, and so on and so on. In parallel, there is a mathematical formula, but you don't need to know that's at A level. But basically, the total resistance is always smaller than the smallest resistor. Okay, time to look at the questions. With these questions, what I'm going to do in this video, I'm just going to talk you through the questions, guide you, help you a bit, scaffold some of the questions, and you'll do them by yourself. And then in the next video, so the next lesson will be you working through the answers and just checking how you've done. First one, write and explain how the resistance of a filament lamp changes when the current through a filament lamp increases. Okay, I'm going to give you a little bit of a clue. When we did a graph the other day, we had voltage, we had current, and the shape of the graph looked like that. There's a reason why the shape of the graph looked like that. It's linked to the resistance and the current. So write and explain how the resistance of a filament lamp changes when the current increases. Look what's happening. This is the current increasing. Can you use that information? Check. Pause, answer the question. Next one, match the component in the list of each of the statement A to D. So there we go. We've got A, B, C, D, and we've got 1, 2, 1, 2, 3, 4. Which of these is a resistor? Which is a filament lamp? Which is a diode? And which is a thermistor? Its resistance increases if the current through it increases. The current through this is proportional to the potential difference across it. That sounds like a law. Did we have a law at any point? Its resistance decreases if its temperature is increased. This one's talking about temperature. Which one has a temperature-related resistor? Its resistance depends on which way round it is connected in the circuit. Again, this one's looking at those graphs. So, again, pause, maybe look back in your book from the previous couple of lessons, which ones match. So, is write A, B, C, D, and then right next to it either diode, filament lamp, resistor, or thermistor. Go. Okay, sketch a circuit diagram to show two resistors P and Q connected in series to a battery of two cells in series, with each other in the same direction. And So you just got to draw resistors. Remember what the symbol for a resistor looks like. Remember a cell looks like this, but it's a battery of cells. There we go, simple. In the circuit for part A, resistor P has a resistance of 4 ohms and Q a resistance of 6 ohms. Each cell has a potential difference of 1.5. Calculate the total potential differences of the two cells. So when you put the two cells next together, you make a battery. What is the total potential difference across that? What's the total resistance of the two resistors? In the starter, we did a thing about the rules of resistances. What happens when you add them together in series? What happens when you add them in parallel? What is the current in the circuit? There we go. Worked out the potential difference. You've worked out the resistance. Here's an equation. Work it out. And what's the potential difference across each resistor? A little bit trickier. But remember, what's the rule for current in a series circuit? I've given you lots of help there. Carry on. Sketch a circuit diagram to show the two resistors R and S in parallel with each other, connected to a single cell. Different version, two resistors, but now in parallel. In part A, the resistor A, R has a resistance of 8 and S has a resistance of 4, and there's a potential difference of 2 volts. Calculate the current through resistor S, the current through resistor R, and the current through the cell in the circuit. Sounds quite complicated, but actually, again, draw it. Remember the rule for potential difference in series. Use that equation. Actually, it's all very simple. There's a funny noise in the background. My neighbours are doing some serious hard work, drilling and stuff. Hopefully you can't pick that up on the mic. Do the question. Go. Done. Splendid. Woohoo, this looks like a proper exam style question. A figure shows a light dependent resistor, LDR, shorthand LDR, light dependent resistor. And it's in series with a 200 ohm resistor and a 3 volt battery and an ammeter. Check. With the LDR in daylight, the ammeter reads 0.01 amps. So it's bright, high light intensity. The ammeter is 0.01 amps. Calculate the potential difference across the 200 ohm resistor when the current through it is 0.01 amps. Just asking you to use the same equation as we've been using for the last few questions, and that is V equals IR. Show that the potential difference across the LDR is 1 volt when the ammeter reads 0.01 amps. Again, don't even have to use that equation. You just use the rules for potential difference in a series circuit. So look back to the rules of potential difference in the series circuit. You'll be able to work that one out. It's a simple, very simple calculation. And then B, calculate the resistance of the LDR in daylight. You know the current. You've just worked out the potential difference. Super easy. Let me put this in a triangle just to help you. B, I, R. If you're doing this question, I reckon it's helpful to redraw that circuit in your book. It makes it so much easier if you've got that to draw around and add things to. B, if the LDR is covered, so it's been in daylight, it's now covered. So it's getting darker. What happens to the resistance of a light-dependent resistor when it's dark? Does it go up? Does it go down? Look back at the graphs in your book. What happens to the resistance of an LDR when it goes dark? So it says if the LDR is then covered, explain whether the ammeter reading increases or decreases or stays the same. I'll give you a hint, it's not going to stay the same. So what's going to happen now is you've changed it, so the resistance of the LDR is going to change. Now, if the resistance of the LDR goes up, it's like more of an obstacle. What's that going to do to the current? Those things that are traveling through, are they going to find it harder if there's a harder obstacle? If the LDR resistance goes down, what's going to happen to the current? They're going to find it easier to pass through. Part 2. Explain how the resistance of the LDR can be calculated from the current I, the battery potential difference V, and the resistance R of the LDR. Just done for the previous question if you knew. So, once you've worked that out, nice and simple. In question 5, the LDR is replaced by a 100 ohm resistor. Let's go back. So now we have a 100 ohm resistor here and a 200 ohm resistor there. And a voltmeter is connected in parallel with this resistor. So now, just at A, draw the circuit diagram. Really simple. Copy the other one, but just switching the LDR for a 100 ohm resistor. Then, calculate the total resistance of the two resistors in circuit. If you're not sure, go back to the starter, look at the starter that we did. It tells you how to add or work out the resistance for resistors in series. Once you've done that, you know the resistance in series, you know the potential difference, you can then work out the current through the ammeter, the voltmeter reading across that device, and the potential difference across each resistor. Just the same equation. V, I, R. Figure 7 shows a light-emitting diode, LED, in series with a resistor and a 3-volt battery. We looked at the diode before. Diode, particular device, has a special graph. A light-emitting diode is a diode that gives off light, as it does suggest. The LED in the circuit emits light. The potential difference across it when it emits light is 0.6 volts. Explain why the potential difference across the 1000 ohm resistor is 2.4 volts. That's talking about how to work out the potential difference in a series circuit. You can do that. Once you've done that, part 2, calculate the current in the circuit. Simple. The current for the LED must not exceed 15 milliamps. Milli, standard form. What does milli mean? Millimeters. Can you put that into milli? If it's millimeters, how many millimeters in a meter? Same, how many milliamps in an amp? You can work that out. The current in the LED must not exceed 15 milliamps or it will be damaged. If the resistor in the figure is replaced by a different resistor, R, calculate what should be the minimum resistance of R. Ooh, that's a proper question. We know what the voltage is. We know what the current is, we just don't know what the resistance R is. So there's just two things, V, I, R. You can do that. It just sounds complicated, but actually it's the same equation you've been doing all the time. If the LED in the circuit is reversed, what would the current be? Give a reason. That's really quite simple. There's 3 marks. Nice. Design a temperature sensor that will switch a buzzer on if the temperature is too low. Explain how your circuit will work. Think the symbol for a buzzer is like this. And if not, that'll work for now anyway. And explain how your circuit works. That's it. That's the questions. So, I just want you to try and answer as many as you can. I think that's a reasonable amount of questions to do in what would be a lesson. The next lesson will be me just going through these. So, have a go before you do the next lesson. If you just copy, there's no point. You won't have learned anything. I believe in you. Love you. Bye.